Good morning and welcome. My name is Ryan Paris. I'm the radon coordinator for the Virginia Department of Health, and you're here to learn about radon testing in schools. Hopefully this presentation will give you a good overview of that. We don't pretend that it will make you fully qualified to test from the get-go, but we've referenced some documents you can go to for further information. And this could give you a good start and might allow your school districts a way to save money over hiring a professional if you do want to get into radon testing yourself. I'd like to introduce Dr. Paul Houle, Professor Emeritus of Physics. He represents University Educational Services out of Mount Pocono, Pennsylvania. He is very experienced in radon. He's been doing radon training since 1986. He does this sort of thing all the time. He's also the current serving president of the National Radon Safety Board, which is one of the two national bodies that certify radon professionals. And he's going to be your presenter today, so without any further ado, I'll turn over to Dr. Houle.
Thank you, Ryan. Appreciate that. If you take a look at this first slide right here, the radon measurements in schools, this talk is based to a large degree on the document titled exactly that, Radon Measurement in Schools, put out by the EPA, and you'd want the most recent edition with what are called the corrections page in it. So if you have that, that's a good document to have in front of you. And in this program, we're going to base much of our presentation on that document, but since the document was published, we've had the opportunity to test a lot of schools, and we've picked up some practical experiences which help to define more clearly some of the things in that document, and we're going to give you that information as we go along today. So in this first slide, I'm just showing you what it is we're going to discuss for the next hour and a half or so, the order of the presentation. I'm going to talk a little bit about what radon is. I'm going to try to motivate you to caring about the radon problem. It is a significant issue, as you will see. We're going to look at the occurrence, how frequently it happens, and what the document covers, this fourth bullet, protocols for testing. That's the recipe that tells you how to go into a school building and do the testing. Nature is a slippery beast, and in order to get good results, we need to be very careful and very rigorous about how we proceed in doing measurements. So we're going to look at that. We're going to look at those protocols, and when you get the results, we're going to look at what do you do with the results? What do they mean to you? What kinds of secondary things should you do? And in that light, we're going to look up we're going to review the follow-up measurements that you will need to make, and what are some of the strategies for performing mitigation. Now I'm going to start with the EPA's map of radon zones. EPA has done a wonderful job in producing this map, and it points out the areas where the potential for radon is the greatest, something in the marginal area, and then something in the low areas. Now in this particular map, the red areas, which are called Zone 1, are the areas where the radon concentrations on the average are expected to be above 4 picocuries per liter. And I'm going to talk about that specific number. The 4 picocuries per liter is called the action level in the United States. And EPA's recommendation, and the industry has taken it to heart, is that if the radon concentration is 4 or more in a given building, then something should be done in order to mitigate that problem. In the orange sections, or magenta colored if you like, the radon concentrations on the average are expected to come out to be between 2 and 4 picocuries per liter. And in the yellow areas, such as, for example, most of Texas, in those areas, the radon concentrations are expected to be below 2 picocuries per liter. Now, those are average values, and it's important to recognize this, that if, for example, you take a county in Texas that's in yellow, that map is telling you that on the average, it's expected that radon concentrations will be between 0 and 2. This does not mean, and should not be interpreted to mean, that, well, we don't have to test in Texas because there are no values. The EPA's map saying there are no values that are going to be above 4, and that's not true. It's the average, and it's an expected value. In fact, this map is called the potential map of radon zones. We can take a look at the state of Virginia in particular, and you'll notice that the red zones are very geographically delineated. And so here in the red zones, on the counties that are in red, the radon concentrations are, on the average, are expected to be above 4. You see way over to the east side of Virginia, along the coast, the averages are expected to be between 0 and 2. And I want to reiterate, I want to underline the fact that the only way to know if you have a radon problem in a building or room is, in fact, to make the measurement. That's the only way you're going to know. Now, some of the properties of radon are helpful and some are not helpful. The fact that radon can't be detected by the human senses, it's colorless, odorless, tasteless, this means we can't see it. And if there were radon in this room right now, I wouldn't be able to tell just by sitting here in the room. And so that is actually a drawback, because if radon smelled like the smell of rotten eggs, for example, and there was a pretty good concentration of it in here, we'd do something about it right away because we wouldn't be able to stand it. But because we can't detect it with our senses, we can't note it that way, and it's easy to ignore. The drawback of radon is, of course, it's a radioactive gas, and that makes it unhealthy for us. I'm going to say more about that as well. It's widely prevalent almost anywhere in the United States. If you dig down a foot or two in the earth, actually even just a few inches down into the earth, and put a radon monitor down there, you will find radon gas. It's pretty pervasive. And not only is the radon dangerous, it produces other radioactive elements. So when the radon decays, by virtue of its radioactivity, it produces other elements, and they too are radioactive. And that's problematic for us. And they are a soil gas, and they can percolate into buildings and produce very high concentrations indoors. Now, this is a Class A carcinogen, and the communities have decided that there are several classes of carcinogens, Class A, Class B, Class C, and Class A is the one that we are most certain produces cancer, and radon is a Class A carcinogen. You'll notice in the first bullet here that it is radioactive, and I'm trying to give you a physical sense of what we mean by an element being radioactive, and that is if you have some of these atoms of radon, say, in your hand, periodically and with regularity, one of those radon atoms will spit out a little pellet, a little bullet, and those bullets are called sometimes alphas, some of them are called betas, and some of them are called gammas. Now, it actually can put out other things as well, but those are the three predominant ones that I'm going to talk about in a little bit. And it's not the atom itself that causes us any damage. It's the little bullets that it puts out periodically, those alphas, betas, and gammas. Those are the ones that cause us damage. Now, it is also an inert gas, and by that, I mean it doesn't react, as you see here in this bullet, it doesn't react within the soil, but it actually doesn't react with any other elements. The fact that it's an inert gas, for those of us who might be chemists or physicists, we'd say the outer shell of electrons is completely full, but the truth of the matter is it just doesn't react chemically with anything, which makes it a very slippery element. It can move around quite easily because it doesn't get involved chemically with anything else that it might run into. And you can see down in the third bullet, it is the #1 cause of lung cancer in non-smokers and the #2 cause of lung cancer in smokers. We all know what the #1 cause of lung cancer in smokers is. Now, I'm putting up here the radioactive decay chain for uranium-238, and you'll notice that It starts at the top. Terrence, could I get you just to make this work a little better for me? I can't get it to work. You'll notice in the upper part, where it's got uranium-238, and the uranium-238 decays straight down into thorium, which is the element directly beneath it. And you'll notice there's a little symbol of alpha in the arrow that comes down from uranium to thorium. And that means that the uranium-238 decays into thorium by the emission of an alpha particle. And then the thorium, that decays down into palladium, by the emission of a beta particle. And a little minus sign next to the beta particle is just to indicate that's a negatively charged particle, not particularly important to us. The palladium decays into another form of uranium, et cetera, all the way down the decay chain until you get to radon. If you follow the radon decays by the emission of an alpha particle to polonium, and then polonium to a form of lead that's radioactive, et cetera, until you get down to the last element on the right bottom, the lead-206, and that's a stable atom. That one is not radioactive. Now, I want to point out that the uranium-238 was placed in the Earth at the time that the Earth was generated, which is about 8 billion years ago. And in that process, in that process, when the uranium was put in the Earth, it began decaying, et cetera, and it provided all of these elements here. And these are kind of interesting, because if you look at all of these elements in the decay chain, they're all solids, every one of them, except for radon. Radon's the only gas. Now, the uranium starts off within the Earth, and you don't have to go down deep into the Earth to get to uranium. And as the uranium decays into all these other elements that you see in this table, they're all solids, except for radon. They're all solids, and so they're stuck in the Earth. It's not easy for them to move around or propagate. However, the radon, because it's a gas, that can propagate itself upwards and out into the atmosphere. Now, radon's not the only soil gas. There are lots of other soil gases. The interesting thing to note is that the soil gas pressure just beneath the surface of the Earth, the soil gas pressure is actually higher than the atmospheric pressure by a little bit. Not by a lot, but by a little bit. And so that pressure in the soil gas drives these gases into the atmosphere. And in fact, if you were to measure the radon concentration outside, if I went outside this building right now and made a measurement, I'd probably get a radon concentration around 0.4 picocuries per liter. And so the gas is percolating up through the ground and into the atmosphere. Now, if you put a building right on top of it, the gas has the opportunity to get into the building. If there's not much ventilation, for example, then the radon concentration in the building can get pretty high. Well, I've expanded this a little bit just to show you now this is the immediate parent of radon, the radium here. And it decays, as we saw a moment ago, into radon, which decays into polonium. And then it has, the polonium can decay in either of two ways, either to this form of lead or to astatine, et cetera, and you can follow all these fellows down to where you get stable lead-206. I've hash marked a little bit the short-lived radon daughters, and I want to talk about the life of these elements. But you'll notice the polonium here is what we call a half-life of roughly 3 minutes. This bismuth, a half-life of under 20 minutes. This particular form of polonium, a half-life much less than 1 second. I'm going to just take a minute talking about the half-life, because half-lives are mentioned a lot in the radon industry. And a half-life is a very easy thing to know about. There's nothing tricky about it. Half-life is a measurement of time. It is the time it takes for half of the atoms to decay, the time it takes for half of the atoms to spit out an alpha, beta, or gamma particle. And if I were to take here, I've got a little soda can here, but let's assume that this is a 1 liter bottle. All right, so in your mind, imagine this to be a 1 liter bottle. And let's say that we put 1,000 radon atoms in here right now. After 3.82 days, you see here the half-life's listed as 3.82 days. After 3.82 days, instead of 1,000 atoms, you'd have 500 radon atoms left. Now, you have a lot of its daughter products in there too, but I'm talking just about the radon atoms. So if you start with 1,000 radon atoms, after one half-life of 3.82 days, you'd have 500 radon atoms. After another half-life of another 3.82 days, so roughly 8 days would have gone by, you'd now have 250 radon atoms. And another half-life, a third one, you'd be down to roughly 125 radon atoms. And so the term of a half-life, which we'll be using, is simply the amount of time it takes for half of the atoms to decay. Nothing too particularly tricky about that. These atoms, polonium, lead, bismuth, and this polonium, these fellows here, it's because they're short-lived, means that when you inhale the radon, if you're in a room where the radon gas concentration is a significant number, when you inhale it, the radon atom's going to decay, it's going to emit an alpha particle, and it's that alpha particle that can do the lungs some damage. But not only that, the other ones, say, for example, this bismuth or this polonium, which is produced a few minutes later, once the radon atom is decayed, it too decays, and it decays by the emission of an alpha particle as well. And that alpha particle is going to hurt us. And this alpha particle can also hurt us. So these fellows here can cause us some damage by the emission of the alpha particles. This guy here, thallium, has a relatively short half-life, but he emits a beta particle. And the beta particle's not very dangerous to us. And so you see most of these fellows here are no trouble at all. This fellow, bismuth, he emits an alpha particle, but that's only after the decay chain has decayed down through lead, which is a half-life of 22 years, and that's a long time. So you don't get much of this particular bismuth in your lungs, while you're inhaling the radon gas in a given room. We've been using the unit picocurie per liter, which is an unfortunate unit, and I find it personally a clumsy unit, but it is what we have in the United States. And what it means is that if you have 1 picocurie in a liter volume, that you will have 2.2 atoms decaying every minute in that liter. So if again for a minute you can imagine this to be a liter container, and someone tells you have 1 picocurie per liter of radon in this container, then what that's telling you is that if you could look in here with your eyes somehow and see these decays, these alpha particles coming off from the radon, that you would see 2.2 alpha particles every minute in that liter. So the unit of picocurie per liter is simply that. There's nothing magical about it. It's simply the number of decays per minute per liter. And in particular, I'm going to be quoting numbers pretty continuously through this program, and I'm going to be using picocuries per liter almost all the time, so I'm just going to ignore the picocurie per liter unit. So when you hear me talking about the action level in the US is 4, I'm going to mean 4 picocuries per liter. If I'm going to use a unit different from that, I'll be sure to make a mention of it. But you'll be real comfortable with it in no time at all. Now, the action level of 4 picocuries per liter was chosen in 1986, and you could ask the question, why did we choose 4? Why not choose 0? In other words, why not just make it so that we want to eliminate all the radon? Well, of course, we wouldn't choose 0 because the outside atmosphere is 0.4, and it would become incredibly difficult to get the concentration in a home to under what the concentration is outside. In 1986, we were pretty confident that we could lower concentrations below 4. How much below 4, we weren't certain, but we were confident we could get it below 4. So we decided, well, that's probably a good place to make the measurement, or to make the action level. Also, the concept of false positives and false negatives would be minimized if we made the action level 4. Now, a false positive is an easy thing. Once you establish an action level of 4, then I'll do this by example. Suppose that in this room, we know that the radon concentration is 6. Okay, so we got the best laboratory equipment to come down, and we've discovered that it's 6. And you come in and you do a measurement, and you get 2. Well, that's actually a false negative. It's false because it's on the wrong side of the action level, and it's negative because it's on the low side of the action level. Now, a false positive would be the reverse. Suppose in this room we knew the radon concentration was 2. We know that. And we come down and we make a measurement, and we find that our measurement says it's 5. That's a false positive. It's false because it's on the wrong side of the action level, and it's on the high side. So we call that a false positive. I'll give you one thing just to think about. Suppose we knew the radon concentration in this room is 5, and we come in with a detector and we get a value of 10. Now, is that a false positive or a false negative? And the truth is, it's neither. It's just a crummy measurement. We knew it was 5, and somehow we got 10. But it's not false. It's on the proper side of the action level. One other consideration that can be made in setting action levels is the costs of, in this example, lung cancer deaths saved. And in 1986, the numbers weren't exactly these numbers. These numbers are from an analysis done in 2010. And you'll notice here that the cost for saving a lung cancer death, if you set the action level at 4, the cost in the U.S. is $190,000. And if you set the level lower, 2.7, for example, then the cost is $220,000. These were all motivating factors in establishing the action level at 4. Now, the U.S. is not the only one that's established action levels. Every country that's looked at the radon problem has established other action levels. And you see Germany has set theirs at 2.7, and you can see other values. Switzerland, I quote here because it's pretty high, their action level is 27. In some countries, the action level is set different for older buildings than it is for new construction. But just to give you a sense that in the U.S., the action level is 4. Other countries, the action levels are different. I should also like to point out that the agencies that claim radon to be a problem or recognize that it's a problem some of them are listed here: the EPA, the Surgeon General, American Lung, etc., etc. And this list could be made to go on and on and on. And I had thought of putting a slide in right after this one, which would be completely blank, which would list all of the agencies that don't recognize radon as a problem. But the truth of the matter is, every scientific community that has looked at radon has recognized it as a significant health hazard. So we have the action level in the U.S., which is 4, and the EPA recommends even a little bit further that if the concentration comes out between 2 and 4, that you should consider doing some further mitigation. In the beginning, when the action level was set at 4, we were pretty confident we can mitigate down to below 4. But actually, with just a few years' experience, we discovered we could actually get the action level oftentimes down below 2. So the EPA now recommends, of course, if the concentration in a room is 4 or more, that you should do something about the concentration and mitigate it down. And in fact, if the concentration comes out between 2 and 4, it further recommends that you should consider mitigating the problem. Just some initial data. If you're looking at the nationally, 15% of all the homes are expected to come out to be greater than or equal to 4. That is, if you do measurements in 15% of all homes, you would find that they have a concentration greater than or equal to 4. And these statistics are living up to this. This is, in fact, the way the data is pointing. In Virginia, however, the percentage of homes to come up with a radon concentration equal to or above the action level is somewhere between 20 and 25%. So Virginia is a little more of a problem than the average nationally. Now, some more motivation for why being concerned is the statistics show that about 21,000 people die from lung cancer due to radon every year in the U.S. Now, that number is bandied about quite a bit, and it's gotten to the point where the number is almost, well, second nature, and maybe we don't even consider it a big number. But 21,000 is a pretty big number. And to get it into context, that's the equivalent of one jumbo jet in the U.S. crashing every week and having no survivors. One a week, no survivors. If we had that happening, we'd sure be looking into the aviation community now, wouldn't we? There is expected to be widespread contamination in schools at the national level. That does not mean that every school is going to have the problem, but on the national level, we expect to find schools pretty much in all areas to have, some schools to have a radon problem. And you see here in the third bullet that 20% of all schools will have at least one room with a concentration greater than 4. So statistically, we're expecting to find schools out there with some rooms in them having a radon problem. EPA recommends testing all schools. That's the recommendation. And you're going to see this pervasive in the documents, that regardless of the zone in which the school exists, the only way to know if there's a radon problem is, in fact, to test for that problem. Some schools have been found to have concentrations greater than 100. Now, 100 is a pretty big number. Considering that the action level is 4, that's 25 times, obviously, the action level. And so it's going to be important that we look at the schools and find those rooms that have a radon concentration that's greater than or equal to 4. Further in the national school data, you'll see that about 2.7% of ground contact classrooms will have a radon concentration greater than 4, and about just under 20% of the nation's public schools have at least one ground contact room above 4. So we come out with 70,000 rooms. That's a lot of rooms. That's a lot of people who are at risk to inhaling a radioactive gas. I put this additional chart on here just to give you some more motivation. You'll see that the lung cancer due to radon here at 21,000 deaths per year it is almost the same as leukemia, lymphoma, and it is significantly higher than all of these other cancers that one could be susceptible to. This breaks it down into how many deaths, how many lung cancer deaths there are per year by the different states. You'll notice California's up there at 1,700 and some odd. And let's come down to Virginia, which is where we are. In Virginia, the number here is, I believe, a little under 700. I think that's 693. And it goes to show you how many people in Virginia die from radon lung cancer every year. Now, who can test? The people who can test are those who are certified to be testers, certified testers. And the typical certifications that exist are those provided by the National Radon Safety Board and the National Radon Proficiency Program. In any case, if you're a school district and you want to get your buildings tested, you can go on the appropriate website and find people who are certified to do so. The costs tend to be relatively high. They're $1,000 and up per building. So if you have 10 or 15 buildings in your school district or more, you can easily see what the cost is going to be. It is, of course, easier for the school staff. And I just mentioned that they must be NRSB or NRPP certified.
Did we have their websites anywhere on there?
I don't.
Okay.
You can go to NRSB. Ryan's just mentioning to me here, do we have their websites? NRSB's website is nrsb.org. And NRPP's website, I'm not quite sure of it, but the name of it is the National Radon Proficiency Program. And I'm sure if you just search for that, it'll pop right up for you.
It's nrpp.info, I-N-F-O.
Okay, great. Thank you, Ryan.
Yep.
Now, so you can do it with certified testers, and the biggest issue there, of course, is the expense. And especially if you're going to test your schools periodically, if you're going to test them every 4 or 5 years, then the expense is going to add up as the days go by. And I know of no school district who have money to waste. You can also have your school staff test. Your own people can test for radon if they've had some reasonable training. The advantages of having your own school staff is the costs are clearly much lower. All you have to do is pay for the test kits. And I've got a test kit right here, and I know that you can get these for $7 or $8 a piece, especially if you buy them at 50 or 100 at a time. So that's pretty inexpensive. And you'd note the cost here, I quote, somewhere around $150 per building. So we're really talking 6-7 times less if you have your own people do it. And there are some advantages to having your own people do it. You have control of where and when you're going to do it. Your staff becomes better educated, and aren't we in the business of education? And the staff will become much more sensitive to the testing itself. And that means they'll take better care of the environment while the testing is ongoing. Now, in testing for schools, it's important to recognize that no two school buildings are alike. These are not like homes. School buildings are pretty sophisticated buildings. They have very ornate HVAC systems. Some of them are built on slabs, some on crawl spaces, some over basements, and they're all different. Some of them have industrial processes going on in them, and the ventilation can be all kinds of high pressure and low pressure areas in a school building. So it requires that we pay some attention to some of these issues. So what we've got here, and what we'll embark on, is trying to find those rooms that have a radon concentration in them greater than 4, greater than or equal to 4. So it's a bit of a detective mystery. And if you haven't tested your school yet, nobody knows. And it will be your job to find out where those rooms are, if you have any. I want to show you for a moment how the radon gets into a building. And here I've got a drawing of a house, but this could just as well be a school building as far as the drawing is concerned. And fundamentally, the thing to remember is that the radon is a soil gas. It comes in from the dirt. That's the only way it gets into the building. Well, there is one other way, which I'll mention, but fundamentally, that's the overwhelming way that it gets into the building, is from the dirt. And so you can see here in this drawing, if the radon gas is below the building, get in through cracks in the foundation, and those cracks don't even have to be visible. Remember this, that the radon, I already pointed out, it's a very slippery atom, but it's an atom, so it's incredibly tiny. So you could have invisible cracks that you can't see with your eye, and the radon can come right up through that as if it were a chasm. It can come in through expansion joints. It can come in through utility openings. If you have pipes, conduits that have wires going in them, come in through the basement, and trust me, if you're a school, you do. Those are never airtight, and so the radon gas can get in through that way. You can even get the radon gas to come in through water, which I'll mention only briefly later. It's not a predominant way of getting radon to be a problem in a school building, but it can come in with the water that comes into the house or the building. HVAC has a big effect on the radon concentration in a building. And I've listed here all of the possibilities that an HVAC system can have. It can increase or decrease the ventilation, and it can pressurize or depressurize the building. That's it. There are no other choices. And we're going to want to pay attention to that, because I want to point out again, for just a moment, it's a soil gas, and the soil gas pressure is just a little bit more than the atmospheric pressure. So if your HVAC system is pressurizing a room, that is making the air pressure in the room just a little bit higher than normal, then that can stop the radon from getting in. And if the HVAC system is depressurizing a room, well, it even makes it easier for the radon gas to get into the building. So we're going to pay attention to HVAC systems. I want to talk for just a moment on the detection tools that you have. These are the 5 that are listed in the EPA document, and I've got examples of the most important ones here. There are charcoal canisters, of which there are several types. This is a charcoal canister. This is a charcoal bag. This is a liquid scintillation device, which also uses charcoal. I didn't bring alpha tracks or electrets, but I did bring a continuous monitor, which you see right here, and I'm going to talk about these devices a little bit and how they work and how we have to be concerned about them. Now, charcoal is a great absorber of gases, all gases, not just radon, all gases. And that's the way this is going to work. Here I've got a charcoal can, and the way you can activate it, I don't know if you can zoom in on this, Terrence, but if you can, the way you activate these charcoal cans, you'll notice there's a paper lid on it, is you just peel that off. Boy, that is good. And now this can, which I think you can possibly see the holes in it, just barely. There are perforations in the can. And as soon as I pulled off the tape, the air from the room is going to diffuse into the can. Now this is filled with just charcoal. That's it. And the radon, the gas radon, will absorb onto the charcoal. And you're going to deploy this for a few days, 2, 3, 4, 5 days. And you can always check with the lab when you buy these, how long should I deploy them? The EPA has a recommendation, but you can check with the lab, say, what's the maximum length of time I can deploy them? What's the minimum length? I can tell you right now, the minimum length is always 2 days, 48 hours. That's the minimum. And you deploy that out into the room, and after 2 or 3 days go by, and you decide, well, that's as long as I want to leave it deployed. You take another label and you stick it on there, and it's no longer being exposed to the radon in the air, and you send this back to the lab. And then the lab gets it, and they have a way of detecting how much radon was in the can. And they also calibrate back for when it was deployed, how long ago it was deployed, what the temperature was when it was deployed in the room, and the humidity in the room. They have a way to calibrate against all of those parameters. So that corrects for a lot of potential discrepancies. So again, the way to use these is you just pull off the tag, put it out in the room, leave it out for a couple of days. When you're done, put the label back on. You fill out a form indicating the information I just mentioned, dates and times of exposure, for example, and you send it back. That's it. And then within a few days, you'll get the result of how much radon was in the room to which this detector was exposed. I can show you another kind of detector. Here, this is what we'll call a charcoal bag, and inside this container, there's a small bag of charcoal. And the way this is used is just like the canister. You open the bag. At some point, it came in a sealed plastic bag. You open the bag, you put this little barrier in here. I guess you put it in like this, right? Just to keep the bag open. And you just put it out in the room. And after 3, 4, 5 days, you take it out, you remove that little foam piece, you stick the bag closed, you fill out the information as to the start and stop time, and you send it back, and you have to remove this little plastic thing too, this little hanger. And you send that back to the lab, and a few days later, you'll find out what the radon concentration was in the room. The liquid scintillation vials, these little things, they're another way. They are also a charcoal absorber device. And the way this works is it's got a little bag of charcoal inside. And you never take this out. Okay, you don't remove that. But I'm doing it just to show it to you. And then inside there's a little bag of charcoal. Here it is here. That's it. Little bag of charcoal, and that's the absorber. This fits into when you get it, it comes this way. It comes already assembled. And then to activate this, so when you get it, it looks like this. And to activate it, all you have to do is unscrew the cap and deploy it. And now the charcoal in the bag is absorbing radon. The air is diffusing into here from the room, and the radon that's in the air will adhere to the charcoal. And then when this is done, after 2, 3, 4 days, you put the cap back on it, you fill out a form, and you send it back. That's all there is to it. These are easy devices. They're called passive devices, and they are going to be as you'll see in a slide here in a moment, what I call the weapons of choice for going out and making these measurements. Now, one of the issues that I want you to pay attention to is once you've sealed this can back up, remember that the radon is in the charcoal, and it's still radioactive, and it's still going to decay. So if you pick these up, you're done with the deployment now, you've picked them up, and you're going to send them back to the lab, but you forget. So it's a week later when you send them back. Well, after a week, the radon's going to have gone down by roughly 2 half-lives. So there'll only be a quarter as much radon in here as there was when you put the lid back on and sealed it up. Now, most labs can calibrate against that, and they will still be able to come up with a radon concentration. But if the radon concentration is really low in the room, then you're going to have very few radon atoms in here when you send this back to the lab. And they may have a hard time with these statistics. So to get the statistics as good as you can, the thing to do is once you put the label on it, send the thing back to the lab on the same day so that your radon concentrations in the canister are as high as they can possibly be. And that's true no matter what kind of a charcoal device you use, whether it's one of these devices called liquid scintillation or one of these devices, which operates very much like the charcoal can. I just mentioned these. These are your weapons of choice, the test kits, the LSC vials, or the bags. Any one of those make great detectors. They're easy to use, they're relatively light, they're easy to ship, requires very little sophistication on the part of the operator. I am going to mention very briefly liquid scintillation. They operate a little differently than the charcoal cans when they get back to the lab. When these get back to the lab, it's kind of interesting. They're put on a detector, and the detector is going to see how much radon is in the canister. Now, how does it do that? Well, interestingly enough, you remember that the radon and its daughter products, they emit alphas, betas, and gammas. The alphas, while they are the most dangerous to humans, to our lung tissues, the alphas can't get out of the can. So when they hit the metal wall, they stop. Same is true of the betas. What does get through the can, though, are the gamma rays. So the gamma rays, they get through the can, and that's what we have in our detector. We have a device that allows it to see gamma rays. Gamma rays are a lot like visible light, just that they're not visible. And so we have a detector over here that the can sits on that can pick up those gamma rays. You can count the gamma rays. And of course, the more gamma rays it counts, the more radon must be in the can. The more radon there is in the can, the more radon there must have been in the room. And we have calibration curves that allow us to convert from the number of gamma rays to the radon concentration in the room if we know the start and stop time of the deployment and the temperature, typically. And that's what we need. The bags, they work very much the same way. The LSC vial works a little differently, just so you have some information what happens to the lab. When this gets back to the lab, a little bit of scintillating cocktail is added to the vial. Now, that's not a martini. That's a liquid that's put in here. It's an oily film, in effect, that's put in. And when the alphas decay, when the radon decays and emits the alpha particles from the radon and its daughters that are adhering to the charcoal, they hit that liquid, and it causes the liquid to excite and emit ultraviolet light. It's not quite ultraviolet, but I'm going to call it that. It emits ultraviolet light. And then we have a detection mechanism that looks for the light. And again, the more light it sees, the more radon's in the charcoal. The more radon in the charcoal means there must have been more radon in the room. And they're calibrated for that. One of the things I like about LSCs is that they can be done with very little manpower in the lab. They can be analyzed without much manpower. Now, that's no advantage to us out in the field, but it is an advantage to the lab. And I put here, just for a moment, a slide of an LSC machine. These vials are located and placed into these racks right here that you can see some of them. And once you load them all in the racks, then you just hit start. And the machine moves all of these racks forward and over to, and then each vial separately into what's called an elevator. The elevator takes it down into a lead shielded area, and where there are photo multiplier tubes which count what I call ultraviolet light that's given off by these. And then the reports are they'll come off, you can see a little computer here. The reports will all be printed automatically. And so the nice thing about this for the lab is, let's say you get 200 or 300 of them in one day, you throw them in the LSC machine at 5 o'clock at night, go home. Next morning you come in, all the reports are printed out and ready to be sent. It's a great device in that regard. Alpha tracks can also be used, and I've got one right here. I brought a sample of them, actually the one in the picture is the one that I have right in front of me. And the alpha tracks work a little differently than the charcoal canisters. They don't absorb anything. And I'm going to open this little alpha track detector. You never open it. When you get it, you just deploy it, you hang it. You can hang it from the ceiling, put it on a table, etc. But I'm going to open it so you can see what's inside. You should never do that. And you'll notice that there's just a little plastic strip inside. And the way this one works is it sits in the detector. Bear with me here. It just sits in the detector. That's it. And you probably can't see it, but there's a little split in the plastic here, and that's how the air diffuses in the room into this chamber, into this little small space. Then when the radon decays, excuse me, when the radon decays, it emits the alpha particles. If the alpha particle hits the plastic strip, it leaves a scratch, and the scratch is permanent. So what we do is we deploy this, and when we're done, we send it back to the lab. And what the lab does is it takes out the plastic strip, and with a little bit of treatment, it can see the scratches, and then they count the scratches. The more scratches, the more radon must have been in this chamber. The more radon in this chamber, the more radon there must have been in the room. And they're calibrated in order to be able to determine the radon concentration in the room. Now, the interesting thing about this chamber, this detector, is that little plastic strip has to have a lot of scratches in order to have good statistical results. And in order to get a lot of scratches, it has to be deployed into really high radon concentrations or low radon concentrations for long times. So this is usually deployed for 3 months at a time or more. It's not usually used like the charcoal canisters, which are 2, 3, 4 days. These are long-term detectors. Also, there are continuous radon monitors, which are not used too much in at least the initial screening measurements for radon testing. But what I have on the slide is a Pylon AB5 monitor. It was one of the first ones out for doing radon measurements. And the nice advantage about these devices is that they can print out an hourly measurement of the radon concentration. When you deploy a radon charcoal can or a charcoal bag, for example, these will come out with values, good values, but they're an average over the deployment period. So if you deploy it for 3 days, you'll find that, well, you got an average over those 3 days. And that's going to be important to us here in a minute. But the nice thing about these continuous monitors is they'll produce an hourly value, and you'll be able to see how the radon concentration fluctuated during the period. Now, these radon detectors, $7, $8, $9 a piece. And you can deploy a lot of them, and the cost is not very much. The continuous monitors, as this one here, they run in the thousands of dollars. So it's unlikely that you're going to deploy 20 or 30 of these in a school building in order to do some radon measurements. But they can be used for diagnostics later if you find that you have a radon problem. And I'll make a few more remarks about that in a little while. In the continuous radon monitors, you'll see that the radon concentration is not correct initially in the first few hours. I want to go back to that slide. Here's the Pylon AB5, and I brought another one here. This is a Sun nuclear model, and
they're looking at the back.
Oh, okay. This is the Sun nuclear model, and really the face is what is the most important part. And these provide hourly results. And the way this works is there's a small chamber in here that is what we call a solid state detector. And the way it works is I take this out of my car, I go into the room, I put it into the room, and I turn it on. And the room air diffuses into that chamber, And after a little bit of time, that chamber is filled with room air. Initially, of course, it has the outside air in it because I brought it in from outside. And so how long does it take for that little chamber to get filled with room air is a few hours. And so the output might look something like this. And so you see in this example here, the initial value came out to be practically 0. And then it went up to 2.5, et cetera, and it grew to a value where it got pretty level at about 4. So the first few hours of measurements we usually throw out. So even though these, if you were using them for a test, would have to be deployed for 48 hours, that's the minimum for all our detection devices, that's the minimum. These, the first 4 hours, we discard that data, simply because it's not representative of the air in the room. And of course, the data jumps around a lot more than shown in that graph, so I've labeled that graph as idealized. Now we're actually getting into the protocols, and this is probably the most important part for those of you who are going to do measurements in schools. And I want to tell you again that, as I said earlier, nature is a slippery beast, and she will do everything in her power to prevent you from coming up with the right values. So we have to be careful. And EPA has come up with a protocol that I think is excellent in doing these measurements and giving us a great chance at getting good values. And initially, there are 2 steps to making measurements in school districts. We will have a screening measurement. Just like in medicine, there are lots of screening measurements for all kinds of things. We'll have a screening measurement whereby we want to go into the school and quickly, relatively quickly, find out if the radon concentration in the rooms is a problem. We don't want to take 2 years, 3 years to find that value. We want to find it promptly. And then we're going to do a second measurement, typically a follow-up measurement, to confirm our original value. So the initial measurement, that can be either a short-term measurement or a long-term measurement. EPA recommends, and rightfully so in my mind, that the first measurement should be a short-term measurement. You'll see that's between 2 and 90 days. And the reason for a short-term measurement initially for screening is if you have a room with a lot of radon in it, we don't want to wait a year to find out that that's the case. We'd like to find out promptly. And so typically the first measurement that's going to be made will be made with one of these passive devices, something like this or like that, and we'll deploy them for 2, 3, 4, 5 days. Now, you'll notice in this slide, the short-term measurement, 2 to 90 days, really you're going to see short-term measurements are 2, 3, and 4 days, maybe 5. We're going to test all the frequently occupied rooms in contact with the ground. Now remember, the motivation for this is that radon is a soil gas, and it's going to get into the building by coming up through the ground. So if you have a 3-story building, for example, the radon concentration most likely will be highest on the first floor, the floor in contact with the ground, and we expect the concentration to be less as we go higher. Now, there may be exceptions to that, but rarely so. I mean, if you had an HVAC system that was drawing a lot of air from the first floor and pushing it up into the second or third floor, it would push a lot of radon with it as well. But typically, the first measurement, the screening measurements we're going to do are going to be down in the lowest levels, those in contact with the ground. We're going to test all the rooms. I put down here simultaneously, but I don't mean exactly simultaneously. I mean on the same day. So if you're going to test 30 rooms in one building, you're going to go and you're going to deploy the first detector in the first room, and then you're going to walk over to the next one, and you're going to deploy the second detector in the second room, et cetera, et cetera. So I really mean just all on the same day. We're going to do it during the school year, and preferably during the heating season. Now, we want to do it during the school year because we want to know what the health risk is to the people in the school. If there's a lot of radon when there's nobody around, then there is no health risk to that. The health risk exists only when the people are around, so we'd like to know what the concentration is while the people are around. So we want to do it during the school year. And we want to do it during the heating season, the reason being that that's the case where we are most likely to have the windows and doors closed most of the time. If you try to do it in the summertime, and students and staff are opening windows, then any radon that gets in the room will be diluted significantly by air from outside. So do it during the heating season, gives us our best shot at getting the radon concentrations in the room without things such as dilution from the outside air. Whoops. Okay. Now, the initial measurement can also be a long-term measurement, and Ryan here mentioned to me that a number of school districts in Virginia have done it with a long-term measurement to start. But the EPA recommendation is to start with a short-term measurement. And so I'm not going to go through very much on the long-term measurements that you can do for an initial measurement. EPA recommends it, and I strongly agree that the first screening measurement should be short-term. Now, if the initial measurement is short-term, and I'm going to make the assumption in this program that it is the right thing to do. If it's short-term, then we'll have some rooms that may come up with concentrations greater than 4. For those that are greater than or equal to 4, we're going to do a follow-up measurement. Now, you might like to jump at the chance and say, hey, listen, I found a room and it's got 10. Let's mitigate it right away. That's a mistake. No scientist would ever suggest to you that you've got one value and you're going to make a choice based on that one value. They're all going to say, well, let's see if we can reproduce that value. And so the purpose of the follow-up measurement is to check on the screening measurement and see if the screening measurement is right. Now, what are the parameters for the follow-up measurement? What kinds of things do we have to be careful about? We want to do a follow-up test in every room where the short-term initial test was 4 or more. Well, that makes sense. You want to perform the measurement, you want to deploy the detector in the same location and under the same conditions as the initial measurement. And you're going to deploy those detectors all on the same day, one right after the other. Now, if the initial measurement was between 4 and 10, EPA says the follow-up measurement may be either short-term or long-term, and if the initial result was high, that is roughly 10 or more, then it's recommended that the follow-up measurement be another short-term measurement. But the truth of the matter is, most of it is done as follows. The initial measurement is made short-term. We deploy one of these short-term, 2, 3, 4, 5 days. We get the results back. Maybe a week later, we have the results in our possession. We know which rooms are above 4 or equal to 4. And we deploy a second short-term measurement. And that's my recommendation. Make your follow-up short-term. There are some problems with making follow-ups long-term measurements. And there is one advantage. The one advantage of a long-term measurement is that it gives you a better average value over a longer period. The disadvantage is that if you deploy 10 long-term measurements for, say, 8 or 9 months, say the period of the school year, so you'd probably deploy something like these alpha tracks, you have to wonder how many of them will you get back. These are 8 or 9 months deployed in a classroom. And there's always the possibility you won't get them back. There's also the issue of you're going to spend a year, if you put out a long-term measurement, where the people are in this health risk, and while you're waiting to confirm the initial value. And so my recommendation is to make that second measurement a short-term measurement, and the EPA permits for that in their protocol. And then you will take some action based on the average value of the 2 short-term measurements. So suppose your first one is a 5, and your second measurement is an 8. That is, your follow-up measurement a week later is an 8. Well, that gives you an average value. See, 8 and 5 is 13, divided by 2 is 6.5. Gives you an average value between 6 and 7 picocuries per liter. Clearly, that average is greater than 4. And if the average is greater than 4, then the recommendation is, well, you need to take steps now to mitigate the problem. Typically, the first step in a mitigation is you're going to call a mitigator. We're not training you to be testers here, to be mitigators. We're training you to be testers here. So if you find a room whose average value between the initial measurement and the follow-up measurement is greater than 4, then you'll call a mitigator. And chances are the first thing he's going to want to do is see all your test results. And then the second thing he's going to want to do is see the plans for the building construction. And then the third thing he's going to do is do some diagnostic measurements. He'll do all of that before he even starts coming up with a plan for mitigating the problem. He's going to want to know where the radon's coming from. If your follow-up measurement, I'll just make a brief comment, if the result of a long-term measurement as a follow-up is greater than...
All right, by our clock, we're at 10:05. Pick it up again and finish the presentation by Dr. Houle.
Okay, thanks for coming back. We're going to talk about testing per design now, and we're going to look at 4 different designs of school buildings. Those built on a slab, those that have big wide open areas, those built on a crawl space, and those who have a basement. And so slab on grade, and I want you to keep in mind that the radon gas is a soil gas. So the easiest way for it to get into the building is through the soil and directly into the building. So if you're looking at a slab on grade building, here's the soil, and the radon can easily get in through the slab. Even a brand new slab, to a reasonable degree, is porous to radon. Now, which rooms do we measure? We're going to measure, that we're talking about the initial measurement, we're going to measure only those rooms that are frequently occupied and in contact with the ground. So second-story rooms, typically we are not going to test. We're not going to test closets, storage rooms, restrooms, hallways. You can make a judgment call on some rooms. If they're not frequently occupied, there's no health risk there. And so you can skip those rooms. If you're looking at open plan or pod designs, if it's just a big open room, say you're going to test the cafeteria, then you want to have one detector for every 2,000 square feet. So if you have a 10,000 square foot cafeteria or a gymnasium, then you're going to want to put in at least 5 detectors in that space. And of course, spread them out so they sample the air and uniformly across the room. If the open pod design has walls that can make rooms separated reasonably well, then you want to test each of those separated rooms separately. That is, deploy a detector into each of those rooms. Now, if you have a crawl space, you might think, well, the room is not in contact with the ground. However, the crawl space certainly is, and the radon comes out of the soil, can get into the crawl space, and then into the room. So even though the room is not in contact with the ground, it does have an avenue for the radon to get in. So the recommendation is to test the classrooms that are above an enclosed crawl space and measure the rooms directly above the crawl space. Now, I say classrooms. What I mean by here is all the rooms that are frequently occupied. In a basement, this one has one little slippery issue. It says, in addition to measuring all the frequently occupied basement rooms, so you would probably test all the basement rooms that are frequently occupied, but you should also test any rooms on the level above it that are in contact with a room, a basement room, that has not been tested. So for example, in here, suppose this is a storeroom. If this is a storeroom, you're not going to test it. It's not frequently occupied. And this room is not in contact with the ground. So you might think, I don't have to test this room either. But the truth of the matter is, because you didn't test this room, you need to test this room. Okay? So that's the one little issue there. Now, we've talked about which rooms we're going to test. Next, we're going to talk about where in the room do we want to deploy the detector. And I need to tell you that these detectors, they're sensitive to a number of things. They're sensitive to humidity, they're sensitive to temperature, and they're sensitive to a breeze. And so you need to keep them out of regions that have unusual temperatures, unusual humidities, or winds, or breezes. And so you got to keep them away from drafts resulting from heating, ventilation, vents, air conditioning, et cetera, et cetera. You got to keep them away from windows, because even what appear to be airtight windows can allow air in from outside. You will get some infiltration. you need to pay attention to putting the detectors where they're going to be left alone. So I don't know if a teacher's desk might be a good place. You might find some teacher's desks, the students are always around the desk. You might find the teacher's desk is a secure place to put them. And you don't want to place them in direct sunlight, because if you place one of these detectors in the sunlight, then they'll get hot. And if they get hot, that's going to affect the amount of radon they can absorb. So you want to keep in relatively room temperature areas. And you don't want to put them in areas of high humidity either. So if you have a laboratory and you have a sink that's constantly running, or an aquarium in the laboratory, you don't want to sit them on top of the aquarium where the humidity might be unusually high. Now, the laboratories that do the analysis on these devices, they're calibrated for humidity, temperature, and they can correct within a certain range of values, but they can't correct if the humidity is really high or if the temperature is really high. So we need to keep them in reasonable values. Now, where do we want to place the detectors? This goes on with, we're still in the room now, and where do you want to put the detector? Well, I want to put the detector where I normally breathe the room air, in case the radon concentration in the room is not uniform, and it's a gas, so chances are it is not uniform. I don't want to put the detector on the floor, because I don't breathe the air that's on the floor. And so I'd love to have the detectors placed right around here, somewhere where my nose is, at that kind of height. So you'll see some of the recommendations here to keep the detectors about 20 inches off the floor, 4 inches from other objects, because we want this detector to be sensing the air in the room as best it can. If we put a lot of objects right in front of it, say put it on a bookcase and put books on either side of it, then that inhibits its ability to sense the room air around it. And you say keep it away from exterior walls, because exterior walls typically are cooler than the room air, and they'll cause ghost drafts, which can have an effect on these detectors. We want to place the detectors, as I mentioned a moment ago, every 2,000 square feet. And then don't fool around with the detector. When you deploy the detector, I like to think I'm going to put it on a table or a file cabinet or a bookshelf. And I like to just put this sheet of paper on the bookshelf, place the detector on top, and I don't know if you can read this, but it says, radon test in progress, don't disturb. And that's part of your anti-tampering device. Okay? So very easy. So you'll have a bunch of these pages with you, and along with your detectors when you go out and make your deployments. When do we test? We've identified the rooms. We've identified where in the rooms. Now we're going to talk about when during the year should you test. Well, you want to test under closed conditions. This means that prior to your deployment, you'd like to have the building closed up for about 12 hours or more if you can get it. And so when's the best time to start this? In my thinking, it's Monday morning. That's the best time to deploy the detectors. You might deploy them before the students come into the buildings. Monday morning to me would be a great time, because typically the building's been closed up for the weekend. You want to deploy them during the colder months, as I mentioned before, to establish closed house conditions, and during the weekdays with the HVAC system operating normally. Whenever you're conducting a 2 to 5 day test, and that's what you're going to be conducting initially, and in most cases with the follow-up measurement as well. Because we want to know what's the health risk on a normal day or on an average day. Now, I put here a graph to show you what the radon concentration looks like. And this was a classroom, and you'll note it started on the 22nd, it happened to be 09, so all right, so that's a little bit old, but the truth of the graph is still true. And you'll notice this was run over a few days, here from the 22nd through the 28th. And look at the radon concentration. Now, the radon concentration is the lower graph. I don't care about the upper graph. It's the lower graph. You'll notice the radon concentration fluctuates pretty rapidly. Down here, it's measured over here on this axis. Down here, it's 1 or 2 picocuries per liter, and then a little later, a couple days later, it went up to around 15 and down around 0 again. You notice the fluctuation is pretty wild. So you don't want to do a measurement for 10 hours or 20 hours or 30 hours. You really want to do a measurement of 2, 3, 4 days. And that way, it'll span the peaks and valleys and give you a reasonable average value. Here's the effect of wind. This was a measurement made with a continuous radon monitor, so it printed out a result every hour. And you'll notice the radon concentration is down around 0 here. The graph's pretty large. In other words, the first tick mark is at 50 picocures. That's pretty high. But it starts around 0, and then we have a little bump up here for some reason, and you'll notice this huge peak of the radon concentration where it goes up to in the hundreds. And what caused that were the winds. The winds outside are indicated here by the blue marks, and you'll notice that when the wind went up, the radon shortly after went up again, went up as well. And the gusts of wind drove up the radon concentration even more. So these are anomalous values in the sense that they're not normal or average. And so when we go to deploy the detectors, we're going to not want to deploy them during high winds, if you're having a thunderstorm, a cold front coming through, low pressure in the area coming in. You want to check the weather before you deploy your detectors. And you also don't want to deploy your detectors when the building is being worked on. The reason is that impacts the HVAC system and the air movement in the room dramatically, which will produce unrealistic and non-representative values for average values. Now this chart here, this one is the hard one to read. Terrence, if we can make this so it's real clear to everybody as best you can. This is the flow chart, which I think is very helpful, and I'm going to go over one of the arms of the flow chart. And you'll notice it starts off here. Make an initial short-term measurement, 2 days to 3 months. Realistically, you're going to do a 2, 3, 4-day measurement in all the rooms we discussed. Frequently occupied, ground contact, during the coldest months. If all the results are less than 4, we come down this left leg, come down here, and we're done. We can consider retesting in the future if we so choose. If some of them are higher than 4, and typically we don't find schools that have a radon problem to have the entire school building with a radon problem. Typically we have 2, 3, 4 rooms turn out to have a radon problem. And so we might have only a few rooms, and that would be my expectation in most schools. If the initial measurement is greater than 4, you have a choice of doing a follow-up either short-term or long-term. My recommendation is to do another short-term test. And do it in the same location and at the same time. So if you deployed them on a Monday for your screening measurement, you get your results a week later, then I would suggest waiting till the following Monday and deploy your follow-up measurements. And then you take the average of the two, and if the average of those two measurements in a given room is greater than 4, then you get your mitigator involved, and he's going to do diagnostic testing and take steps as I've described before, and mitigate the problem. And after mitigation is done, he'll do a post-mitigation test to make sure that the mitigation has worked. I won't even go down the arm for, just to save a few minutes, I won't go down this right arm. If you do a follow-up measurement that's long-term, you can follow it down here pretty much on your own, I think. But that's a nice flow chart to give you some guidance as to the steps to follow. Now, how quickly you should mitigate? Clearly, if you've got a room concentration that's 100, you want to probably mitigate that one right away. If you have a room concentration that's 4.5, I think you want to mitigate that, but you might not feel the same pressure of mitigating really fast. If you have room concentrations, EPA says if the room concentration is above 100, you might want to call your state radon office, you might want to call Ryan, and get some guidance from him. My suggestion is if you're looking at 50 or more, I think you'd want to call Ryan and get some guidance from him right off the bat. And he told me earlier he's very enthused to hear from school districts and with the questions that they have. There's some diagnostic tools that a mitigator can use, and I was going to give you this just to show you some of the things they can use. I'll mention only one here, just in the essence of saving a little bit of time. Here's a device for measuring small pressure differences. So if you want to know the difference in the pressure between in the classroom and outside, you can use these things called micromanometers. They measure very tiny pressure differences. Really low, you might suspect that that's a big part of the radon problem. And maybe an adjustment in the HVAC system can solve that problem in its entirety. But these are some of the things that a mitigator might use. You would not be using these as a tester. I want to show you something about mitigation, not much, but I just want to show you a little bit about mitigation. And there's active soil depressurization, there's an adjustment of the HVAC system, and if the concentration is high, honestly, if you have a concentration 50, 60, 70, I would consider strongly stop using that room until you get this problem resolved. In a subslab depressurization system, this is very easy and straightforward. You need to remember that the gas is a soil gas, and I've got a picture of a house here, but it could just well be a school building. And what we do is we typically cut a hole in the floor, put a pipe in, usually 4-inch pipe, and dig out some of the gravel aggregate under here, and you put an exhaust fan up here above the roof line somewhere, and what you do is you vent the gas out from under the slab before it has a chance to get into the building, and then out. What you're doing is you're lowering the pressure right here, and then the gas will migrate to the pipe rather than into the building. And that's an incredibly effective method. I see numbers on the order of 98% effective, 99% effective. Subslab systems work great. Now, quality assurance. We need to spend a few minutes on quality assurance. And the reason being, we're going to deploy 20, 30, 40 detectors at a time, maybe more. Just think of one of your school buildings might have 30, 40 rooms on the lowest floor in contact with the ground. You're going to put out 30, 40 detectors. As I mentioned, nature's a tricky little beast, and we need to make steps that allow us to have some confidence in the values that we're getting from the lab. And so we're going to do quality assurance, and we're going to do duplicate measurements and blanks. And I'm going to talk about those. And at duplicates, we're going to do 10% of the devices deployed. So let's say you put out 20 detectors. That means in 2 of the rooms, you're going to do a duplicate measurement. That simply means you're going to put out 2 canisters in the room rather than just 1. When you deploy the first one, you're going to deploy the second one, and you're just going to put them side by side, 4 inches apart, typically, and that's a duplicate measurement. Then we're going to have some others that we're never going to deploy. We're going to get it from the lab, and we're never going to deploy it. We're not even going to take the label off to expose it. And those are called blanks. And the purpose of that is so that we can check on the lab to make sure that this value should come out to be close to 0 when we get it back. The duplicates, if you put the 2 of them in the same room, a few inches apart, they should come out with pretty much the same value. So they should come out, if this one's reading 4.5 and this one's reading 4.8, I'm pretty happy with that. Those 2 values are pretty darn close to each other. But if this guy comes out to be 1 and this guy comes out to be 15, then I have to call the lab and find out what happened. That would be problematic. I want to make some comments on the distinction between precision and accuracy, and it's depicted pretty well by a drawing like this. If your values come out all grouped together, let's say you have a duplicate here, and here we've got 4 values, but let's suppose we had 2. If the 2 of them come out close together, that means you've got good precision, but we don't have any information on the accuracy. And the reason we don't have any information on the accuracy is we don't know what the radon concentration in the room is. That's what we're trying to find out. So the most we can do is get an expression of, do we have good precision? This sample here, this example here, shows that they're all closer to the bullseye, to the correct value, if we knew what the correct value is, and we don't. But they're far apart. They don't produce the same value, so they got poor precision. On the average, they have pretty good accuracy. And that's really all I'm going to say about that, because we'll talk about precision as we go along. Now, blanks, since they were never deployed, should produce values that are close to 0. Laboratories that can't measure down to 0, but can measure down to 0.5 pretty well, will oftentimes report a blank as less than 0.5. That's a fine value. No problem with that. What they're saying is, hey, we know it's less than 0.5. That is, we know it's really low, but we just don't know, we can't state with confidence how much below 0.5 it is. I'm completely happy with a value like that. If a blank came up with a value of 2, or 3, I call the lab and ask them, how could a blank come up with a value of 2 or 3? I'd want an explanation. And you don't deploy the blanks, you don't unwrap them. I'm going to tell you what to do with them in just a minute, but they're not to be exposed. We're going to include our duplicate values on what's called a duplicate log. In other words, let's suppose this one comes back at 5 and this one comes back at 7. Is that a problem? Well, I said to you a minute ago, if this came back with a 5 and this a 5.8 or even a 6, I wouldn't be bothered by that. I mean, they were measuring the same year, but the radon is a gas and the concentration fluctuates a lot. And so a difference between 5 and 6 wouldn't bother me. How about a difference between 5 and 7 or 5 and 8? I want to quantify that difference. And we do that using one of these things called a duplicate log. And I've got one filled out here for you with some information. I'm going to make this as painless as I can. The first value for the duplicate is put in here and the second value here. So we deployed these two into one room, a few inches apart. We got them back together. We got the results back after a few days deployment. The lab gives us the results. And let's say the first one is 1.4 and the second one is 1.2. We calculate the average value and it's 1.3. If you want to know the formula for calculating the average value, it's given right there. If the average value, sometimes called the mean, which is why we put an M up here, if the average value is greater than 4, then we put an X in this column. So here appear values 4.6 and 5.1. They have an average of 4.9, which is more than or equal to 4, so I put an X in here. Same thing with this pair, I put an X. Same here and same here. Let me just point out one thing. If I take D1 minus D2 here, I'm going to get a negative number, a minus 0.5. And we're simply going to ignore the minus sign. Okay, we're going to take what are called absolute values. But you can just forget about the minus sign and calculate the mean without the minus sign. So I'd have 4 columns here whose average values come out to greater than 4. So now what I'm going to do is I'm going to take a look. Let me take a look at this one right here. This is where I quantify whether or not the difference bothers me. The average was 4. I take the difference between 4.1 and 3.8, which is 0.3, and I divide that by the average. 0.3 over 4 is 0.075, and then I multiply by 100 and I put that number here. Let me just go over that again. I'm going to be using this formula. I'm calculating the relative percent difference. I take the difference between the values, which in our case is
0.3.
0.3. Thank you, Ryan had to remind me. 0.3. I divide by the average, which is 4. So that comes out to be 0.075. I multiply by 100 to get it to a percent, and I get a 7.5%. I do that for all of the values whose averages came out to greater than 4, and I add them up. It's 49. So if you add up these 4 numbers, you get 49. I take that 49 and I divide it by the 4. So I get an average relative percent difference. So now I'm using this formula. 49 divided by 4 is just a tad over 12. And if that average is greater than 25%, then I'd contact the lab. It's 12% roughly in our example, so I don't have to contact the lab. My confidence in the measurements is good. If the average RPD comes out to be less than 25% and my blanks come out to less than 0.5, I'm a happy camper. My values have a lot of confidence, and if I have to defend them, I can. So there is a checklist to this testing program. You want to plan the testing program, and you need to pay attention to this, and I'm going to go through each step of this checklist. You want to plan the testing program. Remember, you've got to identify the rooms you're going to test. You've got to decide on the number of detectors, which is not equal to the number of rooms, because you've got to have your quality control detectors. You're going to have to decide when you're going to deploy them, what anti-tampering devices you're going to use. You've got to have excellent record keeping. This is so important. I can't underline that enough. You've got to have excellent record keeping. Do not feel rushed when you're doing these steps. You've got to plan on when you're going to pick up the detectors, how you're going to prepare them for the lab analysis to be sent back. You've got to do your quality assurance, and when you're done, I mean completely done, that means your screening, your follow-up measurements, your quality assurance calculations, and your review of that information, then you can send a letter to the appropriate individuals. Now, to plan the program, you want to test in the cold season, consider the holidays. You don't want to test on a Wednesday or a Tuesday when Thanksgiving is Thursday. So you've got to avoid the holidays. You're going to count the number of rooms to be tested and add 15% more for the quality assurance detectors. You need 10% blanks, 10% duplicates and 5% blanks. So if you're testing 20 rooms, you need 23 detectors. You want to make sure you're getting the detectors from an agency that's approved it or a state-approved detector. And you need a simple floor plan. Now, it can be as simple as your fire exit plan. Oftentimes, that's enough. And in order to keep track. In this case here, we define ahead of time where we're going to put the duplicate piers. So we're going to put a duplicate pier in this room and in this room. And I remind you that the blanks are not deployed. But I want to, as you'll see, we're going to keep a record of where the blanks are and when we're going to put that on our log sheet. There's a second log sheet we're going to have to look at. And so we'll put that on this fire exit plan or whatever plan you're using. You're going to choose a location in each room and put this information on the device placement log. And you're going to identify those rooms to be used for duplicates and blanks with a D or B, just as I suggested. And then count the number of detectors when they arrive. Make sure that you receive the right number of detectors. And look at the detectors, make sure they're not damaged. If a detector is damaged, you can't use it. Get another one. Now, this is the device placement log, probably the most important document you're going to have in this whole project. You're going to, here we're testing a bunch of rooms. Here's room number 100. We're going to put the detector on the south wall cabinet. Remember, you're going to go and pick up these detectors 3 or 4 days from now, and if you're deploying 20, 30, 40 detectors, you're going to need a reminder as where the heck did you put that detector in the first place? You're going to write down the serial number, the date at which you deployed it, and the time at which you deployed it. This information you can't put in just yet. We haven't picked them up yet. Now, in room number 100, we're going to put a duplicate. So we're going to deploy a second one. I'm not putting the room number. I need to know that on this log sheet that the D means that that duplicate was put in to this room. Same kind of information is here. Then we go to 102. We put a detector in 102. We put it on the bookshelf. So hopefully that allows us to find it again when we go back to get it in a few days. And the same kind of information. Now here I put a blank. Now we are not deploying the blank. We're not putting it in room 102. But on the log sheet, I have the information for that blank. And you'll see I have some more to say about this particular log sheet. When you go to the room number or name, and we've run into this, you have to uniquely identify that room with a number or name that is definitive and will stay there for a while. You don't want to call it Mr. Jones's biology lab, because 2 years from now, when you want to look at this log sheet and review your results, Mr. Jones will have retired, and now that's Mrs. Smith's biology lab. And that room name will be kind of useless then. So you want to have a unique, well-defined room name. Be careful about that. When you go to deploy the devices, you should notify the students and staff prior to the deployment. Let everybody know you're going to be deploying, or someone's going to be deploying these detectors. You will fill out that device placement log before or while deploying the devices. Now, EPA, I've just gone back to it. EPA recommends filling out where you're going to put it ahead of time. Before you go to the room to actually deploy the detector, go out a few days ahead of time and say, well, I'm going to put it out on the south wall cabinet. I can fill this out ahead of time, and you can. I find it more efficient to just have the detectors in a box with you when you're going to the room, and when you walk into the room, take 5 or 10 seconds and look around the room and say, well, I don't want to put it there. That's an outside wall. There's a vent up there, so I don't want to put it in that area. I want to put it, there's a bookshelf over here. I can put it on the bookshelf, or I can put it on the file. Take 5 or 10 seconds. Once you walk in the room, look around, and deploy the detector where you think it should be deployed and fill it out at that time. It takes just one trip to go and make the deployment and fill that out. You want to deploy all the detectors, one right after the other. And some of the detectors, these plastic bags are great for this. You can hang them from the ceiling. Now, I'm not suggesting you take this and you just hang it on the hanging ceiling because it's way too high. But you might want to put a piece of string up, run the string down, and hang it from the string. So you want to bring with yourself some tape, paper clips, string, and a step ladder. Everything you need in order to deploy the detectors. These can also be hung. These not so easily because they're fairly large and heavy. But these fit well on desks, file cabinets, etc. And the duplicates, they should be placed 4 inches apart. And remember to use that sheet. Radon test in progress. It's the least you can do to help people know that they should not be fooling around with that. Blanks, I underline it again, you do not deploy the blanks, but you record them as if they were deployed. We don't want the lab to know they were deployed. We don't want them having a heads up that we're looking, that we've got a blank involved with our detectors. Then most of the detectors will come with a form that you fill out in the bag model here. The form is right on the cardboard. You just fill that out. It is important that the laboratory not get any sense about which ones are duplicates or which ones are blanks at this stage. The record keeping, this is just so darn important. In the remarks section, you can record any unusual weather information, such as storms, winds, etc. When you go pick up the detectors, you want to make sure you follow the detector instructions. So if you're using these canisters, you want to put that tape on the top. Once you've picked up the detector, put that right on right away. If you're using these, just screw the cap back on. Check them for damage. In fact, check to see if they were in fact where you deployed them. And then you record the dates and times on the log sheet and then sign the log sheet. So the log sheet at this point might look like this. And you'll notice I've grayed out these 2 columns because these 2 columns we're not sending back to the lab. One of the things that the EPA document does not talk about, which I think needs to be put in, is under results, you should list the temperature in the room, the average temperature, so maybe 78 degrees, 68 degrees Fahrenheit, or maybe it's 70 in all of these. But these charcoal detectors need to know the temperature they were in. Even though they're calibrated for temperature and humidity, the temperature is the only piece of information they need. So make sure you get the piece of information as far as the environmental conditions are concerned. When you send this back to the lab, what you're going to do is you're not going to send this whole sheet. You're really just going to make a copy of this sheet, and when you make the copy, blank out these 2 columns. So the lab gets everything from the serial number on. That's the information they need to come up with the radon concentration. They don't need the rest of this information. And also, when you get some of these detectors, like the charcoal cans that I showed you here, they come out with a sheet like this that you fill out the start date, start time, etc., etc. I have found that if you're going to make a school project and test your school, you can tell the lab ahead of time. When you call them and say, hey, I need to buy 50 canisters or whatever you're going to buy, tell them what you're doing. You're doing a school project, you're going to be testing a school, and you don't need these sheets. It'll save you a lot of time if you don't fill them out. But if you want a second copy of data, fill them out, and you'll have a second copy. But really, we have not experienced any problems with labs who were unwilling to accept just this device placement log. Just works great for us, and it'll work great for them. Now, here's a device placement log I put up, and I'm going to give you just 20 seconds to look at it and look at it for errors. How does it look to you? Okay, your time's up. I lied. You're not getting 20 seconds. Take a look at this. Here, if you look under room names, there are 2 room 102s. So there's a problem right there. Now I'm starting to doubt about the entire project. If you look at the times, here's a detector that was deployed on the 15th. Whoops, let's go to this one. Deployed on the 18th and picked up 6 days earlier. All right, well, that's a problem. So these are issues that we have to watch for. And look at this guy. He put a detector above the first ceiling tile. Well, that's a crummy place to put it. How about in corner on the floor? That's ridiculous. That's a terrible place to put it. And then the guy had the nerve to sign it, "I am good." So watch, you can have someone look over your device placement log at some point just to check for these kinds of errors. When you're sending them back to the lab, you want to do these things. You want to prepare the blanks, that is, just fill out your device placement log or the sheet that the lab gave you. Check the log sheet to be sure it's complete, and then return the detectors. And then usually within a week, you'll get the results. Now, when I say check the log sheet, I can tell you this. If I do something and I've made a mistake, then for me to find that mistake is hard by reviewing the sheet. It's much better if I were to sit here and give it to Ryan and say, "Ryan, would you look this over?" A pair of fresh eyes can pick up an error much more easily than my own. And then, prior to releasing the results, you want to check. Now you've gotten all the results back. You've done your follow-up measurements. You've checked those rooms a second time. You've done your RPD log. And you've checked the blanks for values that are below 0.5. You've done all that. You've had a colleague check all your values to make sure that you didn't make an error. After you've done all that, then you can release the results. And your school administration will decide on how they're going to do that. But you don't want to release the results until, in fact, you have checked and double-checked everything. And if you need help with interpreting the results, you can contact Ryan, whose phone number I have here, and his email address. And I hope those now, I'm looking at Ryan, he's saying, yeah, those are the right numbers. And he's enthused about getting calls. Or you can call us. That's our number there, and we'll be happy to talk with you as well. So there is a summary here that I'm going to go through pretty quickly. There's a bunch of things you have to do prior to testing. Establish your floor plan, identify the rooms, count up the detectors, order them. When you call the lab, ask them, what anti-tampering devices do you have that I can use? And they may say, well, we usually recommend these, window seal tapes or other kinds of things. Ask them what they might have. And when they come in, of course, prior to testing, check the detectors when they arrive. You're going to establish your testing dates, check the weather, make sure you let everybody know that you're coming. We've been in some schools where everybody knew and it was great. You went into this, when I walk into a classroom, I go right to the teacher if the classroom is being in use, and I say, "Are you aware that we're deploying a radon kit today?" And when they say, "Yes, we are," it was great. It was never an issue. If we go in a room and go to the teacher and say, "Are you aware we're putting a radon test kit out today?" And they say, "A what? A radon test kit? Is that dangerous?" And now I'm stuck there for 5 minutes explaining all of the issues. So they need to be informed ahead of time. During the testing, really there's not much to do. You have your displacement log sheet, and the only thing you really need to do is, if there's any unusual weather, put that in the remarks section of the displacement log sheet. After testing, you're going to pick up the detectors, check them for damage, fill in the log form, and ship them, and get them out. When you get the results, you're going to complete your log forms, check your blanks. The values need to come down under 0.5. Calculate all your QA/QC. Look for clusters. And this is what I expect that you will find. You will find not room 100 and room 110 having a problem. If you have a problem, you're probably going to find room 100, 101, and 102 all having a problem together. That's what we've been experiencing. Plan for your confirmatory tests, that is your follow-up tests, and after all of that is in, then you can create a report. You know, I sort of skipped a step here right after. Plan for confirmatory tests and have somebody double-check all your values. That'll build your confidence in your results. Now, there are some frequently asked questions that we've had from the teachers and staff. Hey, if there's radon, do I get a headache from this? You know, I've been having headaches. Is that due to? The answer is no. The only health risk we're concerned about in the radon industry right now is lung cancer. And, you know, that's a protracted symptom. It takes years for that to develop. So trust me, it's not going to be a headache or an eye irritation. There's absolutely no risk in handling the detectors. These are, when you get them, these are as clean as anything you're going to get. And they are simply absorbers. They don't add anything to the environment. If anything, they subtract from the environment, although not much. But there's no problem with them. Building materials rarely, but may emit radon. Some sheetrock, some concrete will have radium in it, which will produce radon, and that radon will percolate out of these materials and come into the room. It is not very common, and we have not seen it in a school district at this time. We have seen it in an apartment building, however, but not in the school district so far. And in any case, a mitigator will take that into account when they come down and do their diagnostics. These are the references that Ryan had sent out to you earlier: the radon measurement in schools, self-paced training workbook, radon measurements in schools, and radon reduction techniques. All of those are free and available to you. If you go to epa.gov, just type in one of these titles, and those documents come out, and you can print them out and have them for you there, and so you get them immediately. They're easy to get. I'll briefly go over some mitigation topics. Not that you're going to be a mitigator, but you're going to probably, if you need one, hire a mitigator. Sometimes your own people can take care of the radon problem by adjusting the HVAC system. But I would recommend getting a mitigator on board and have them come down and analyze the whole situation prior to making any adjustments. And if you have your own on-site personnel taking care of these things, that's great, because then they can check it regularly if they want. They can check the pressure difference between inside and outside on a regular basis. In fact, you might even want them to have them do that every 6 months or so, just to make sure that the HVAC system is running in such a way as to minimize the radon problem. Schools should be community leaders. They really should be. Mitigation goals. The goal here is to get the concentrations down below 4. That's the goal. And mitigators today can do that. In the radiation industry, we go on the principle of ALARA, which is to get things as low as reasonably achievable. And while mitigators can regularly get the concentration down below 4, they can often get the concentrations down below 2. And they should be shooting for that. Mitigators recognize schools are not houses. They're used differently. They're built differently. They're complicated. Schools are really ornate structures. They have complicated HVAC systems. They have elevator shafts, industrial processes. And that means you need to get a mitigator who hopefully has large building experience. And there are mitigators out there who have that. Now, the radon, I'm going to take just another minute or two talking about how the radon gets in, but I think you already know how the radon gets in. It's a soil gas, and it's driven by pressure into the building, because the pressure in the building is less than what it is outside. I showed you a graph where the wind can cause the pressure in the building to go down, and making it easier for the radon to come in and augmenting the radon concentration by orders of magnitude. If there's a low pressure that comes by, that's self-speaking, if the barometric pressure outside goes down, the pressure in the building's going down. Again, making it easy for the radon to come in. If you have, say, some chimneys or furnaces that are operating in a basement, for example, and they're taking air from the basement for the combustion process and then passing that up through a chimney, then they're going to lower the pressure in the basement, and that's going to get more radon into the basement, and therefore more radon into the building. And just if you have large exhaust ventilation fans in houses, a whole house fan can bring the radon up easily by orders of magnitude. And school buildings may have similar kinds of fans that do the same thing. Here you can see I've tried to show that the radon concentration underground is higher. I don't mean to say it's positive and the air pressure in the basement is negative, but they're simply higher than what it is in the basement. If you put a subslab depressurization system in with an exhaust fan here, notice what it's done. It's lowered the pressure in the ground so that it's lower than what it is in the basement. And that will diminish dramatically how the radon gets into the building. Here's a sample of a temporary system put into a school building for radon mitigation. It's just temporary. It's a sub-slab system that was put in. You sure hope that this isn't a permanent system. This is a temporary system just to see if two exhaust fans together, two radon fans together, would lower the radon concentration in the building. You can use temporary systems for diagnostic purposes or for getting high values down quickly and to test if this is going to work. Why put in a mitigation system neatly with the attending expenses of that if you can do it cheaply just with a temporary system and see if that's going to solve the problem? Here's another temporary system. This is what it looks like from outside. All temporary, but the idea is this going to work? Results oftentimes can be less than 2, which is a great result. Good mitigators can manage this. Here's a permanent system. You can see the roof of the building with 2 rooms being mitigated with an active soil depressurization system. Another picture of that. Just another picture. 1 radon fan in this particular case above the roof line. Not unattractive. Here's the penetration through a rubber roof. Neatly done. Here's a radon vent pipe going through an unheated space, and so it's insulated to diminish condensation. They're always labeled. They have to be labeled a radon reduction system. Now here's one school. I won't even tell you the state it was in, but one that was found to have radon, and you'll notice this is a nice example of a cluster. The radon concentrations, after they were received from the lab, were put on the floor plan, and they were put in values. So you see here 2.5, less than 0.4, less than 0.4. But you look here, 7.6, 32, 5.6, etc. You notice there was a cluster of values, which is what we typically see. Everything to the right is a problem. Now, unfortunately, I couldn't get the red line to just sort of square off and get this little piece in. But it's everything effectively to the right in this here. One mitigation exhaust pipe is able to solve this entire problem. So a good mitigator will look for clusters like this. And you can do, if you're putting up a new building, you can put in a sub-slab system as you go along in the construction. And it's called radon-resistant new construction. And if you have a radon problem, they can be activated and solve the radon problems quickly. Here's a new school building being put up. And here's a fellow putting the radon mitigation pipes together ahead of time. He's going to put this in. It's going to go in under the plastic. Here's the pipe is put in within the gravel, and the plastic vapor barrier will be put, of course, on top of that, and the concrete will be poured on top of that. And this is stubbed out. So the nice thing about this is this perforated pipe goes out quite a distance in either direction. And so if you turn that on, it's in a very effective depressurization system for the gravel and draws the gas out quickly. And that's our job, to save a life today. You can do it, and you should. Thank you.
Thank you, Dr. Houle. We've got a few minutes left. There you go. I realize the down factor about this presentation is we don't have any live interaction with you. We just couldn't design it in a cost-effective way to allow that. So I'm sure some of you might have questions, so please either call or email me or Dr. Houle. You've got his contact information as well. I think what we'll probably do is I might be able to put all of the most common questions together along with answers and then route that through DOE so you can get a hold of that, the most common questions and the answers. And this presentation will also be preserved. We're probably going to start up putting it on the VDH website, and we'll get that information to you so that you can access that in the future. Unfortunately, because of scheduling, we've got the National Radon Conference coming up. It starts this weekend. So I am probably going to be in the office all day tomorrow, and then I'll be out of the office for about a week. So answers to your questions are probably going to be delayed somewhat. Yeah, Hunter?
One of the frequent questions we get, Ryan, is that if we've done testing, do we have to do testing again? And my standard answer back, yes, you would need to do testing again if you were occupying a new space, if you were going into, it's going to become habitable. Would you want to expand on that? And
the code as it's written in Virginia right now only requires school buildings to be tested once. Now that's rather unusual. Right now there's about 10 states in the country that require school testing. I believe all the rest of them require another set of testing every 5 years. And that's to possibly catch any changes in the building which might allow radon situation to get worse after the building is initially built. We don't have that requirement in Virginia. You're only required to do one test per classroom. So typically what's done, all the classrooms in existence back in the early 90s were done at that time. You should go back in your records, see if you can find those records somewhere. I have a copy of most of the records at VDH. If you cannot find those old records, then you probably should consider going back and retesting your older schools. You need to have copies of testing records for every classroom you have.
And I guess too, Ryan, a follow up on that question, if they're changing an HVAC system, if they're like getting rid of their old one, putting in a new one.
That might be a good idea. I don't know if you would necessarily have to do every classroom in the building if you're changing the HVAC system, maybe just a few random samples to see if it is making much of a difference. You could go back and check your original results. But if you are remodeling, doing extensive remodeling, if you're adding a new wing, if you're building an entirely new school building, all of those need to be tested. So you need to test the new classrooms as they come online. The code does not give a deadline for that, unfortunately, and that's probably why I think a lot of the schools have fallen down and not kept up with it, is there's no deadline in the code. But you really should get that done for every school classroom that you build.
May I make a comment or two?
Mm-hmm.
It's really a matter of just common sense, and that is, if you have a house and you're living on and your house has a well, you should periodically test your well for pollutants and toxins. And I know we do, where our house is on a well, and we periodically test it because we don't know if the neighbor. In fact, one of our neighbors has a great garden. We don't know what he's putting in the soil there, and if that's getting down to our water. So we get it tested regularly for heavy metals and bacteria. Every few years we do that, and it's only common sense that you should do that for the radon as well. I mean, anyway, that's as much I want to say. It's just a common sense issue to me.
And we realize it's a cost factor. Not everybody can afford periodic retesting, but I think in Virginia you've got to keep in mind the code says you've got to do it once for every classroom you have. So that's where you need to catch up if you've fallen behind. Again, I have records of most of the schools. Unfortunately, and this is on us, when we changed buildings back a few years ago, we lost some of the original school testing records. So we're probably not going to have the originals for everybody. And hopefully you do. And again, if we can't locate those original records for all of your older school buildings, you probably should consider doing it again. So I guess that's about all we have. Again, send your questions to me, send them to Dr. Houle. We'll try to put together a document, summarize the questions and the answers. We'll get it out available on the website so that other people who missed this initial presentation can go back and view it. You'll get all that information from Mr. Barnes and DOE, but it might take a week or two. Again, we're going to be very occupied the next week or so. So without any further ado, we're almost right on time. So hopefully this helped and can give you some guidance on letting your people do some of this testing and saving some money that way. That's what our main goal was for this. And we're here to help you in any way we can, so feel free to use us.